Hello there, and welcome to The Perfect Square Solves Calculus Problems. Please subscribe if you find these helpful. And in this section, I'm going to talk about derivatives. So I'm going to do things a little bit different. In the previous videos, I've created videos as if I was going to teach the course. But these are going to be more like tutorial videos. So in these, I'm just going to problem solve for you. So, because I know some students they just want to know how to solve problems. So this section that we're going to start with, it's going to have several videos, and it's going to be under a playlist called Derivatives for Calculus, or under Calculus Problem Solving. I haven't decided exactly the name yet. Okay, so we're going to start with derivatives. Now in calculus, you actually learn that you can find the derivative using the limit of the difference quotient, but we're not going to do that here because that's a nasty way to try to find a derivative. We're just going to start with the basic rules. So the first rule we're going to start with is the constant rule. So if you want to find the derivative of a constant, that's going to be 0. So if your function was 5, then the derivative of 5 is 0. If your function is pi, then the derivative of pi would be 0. And even if your function is some variation of terms, but it's still a constant like 5 pi cubed, the derivative would still be 0 because 5 pi cubed is 0. Okay, now then we have the simple power rule. Now in a later video I'll talk about the general power rule, but the simple power rule basically says if you want to take the derivative of an independent variable to the nth power with respect to that same variable, then that's going to equal n times x to the n minus 1, where n can be any real number. Now n here, so what you do is you just bring the n down as a factor, so we bring the n down as a factor, and then you reduce the exponent by 1. So I'll start you out with a simple example here. If I want to take the derivative of x to the 7th, then the f prime here would be just bring the 7 down as a factor, so I'd have 7 times x to the 7 minus 1, and then you just take 1 away from the exponent, so you get 7x to the 6th. Now when you have radicals or denominators and things like that, you're going to have to figure out a way to write them as an exponent. So here I've got a function, the 5th root of x squared. Now I went ahead and converted this to an exponential power here, x to the 2/5 power. So you'll need to know how to do that in order to apply the power rule to problems like this. Now the derivative of this using the power rule, once I've converted it, is 2/5, bring the 2/5 down, and then x would be raised to the 2/5 minus 1. Okay, but 2/5 minus 1 is actually negative 3/5. So I'd have 2/5 times x to the negative 3/5. Now, most math instructors don't like to see negative exponents. So we can easily fix this. All we have to do is move the x to the negative 3/5 to the denominator and then make it x to the positive 3/5. So in the numerator I have 2, in the denominator I have the 5, and the x to the 3/5. Okay, so here's another example. We want to take the derivative of 1 over the cube root of x squared. Okay, well first let me write this radical as a power here. So that would be 1 over x to the 2/3 power. Now since this is in the denominator, I'm going to move it to the numerator, but if I do that, it has to become a negative exponent. So I have x to the negative 2/3. And then when I take the derivative of that, I'll use the power rule. So I'll bring the negative 2/3 down as a factor, and then I'll have x raised to the negative 2/3 minus 1. And negative 2/3 minus 1 is actually negative 5/3. So I have minus 2/3 times x to the negative 5/3. And then just like the previous problem, I'm going to move this to the denominator and change the exponent to positive. So I have minus 2 over 3x to the 5/3. Now a special case of this simple power rule, if you wanted to take the derivative of x with respect to x, well, since x is x to the 1st, if you applied the power rule, you would get 1x to the 0 power, which is just 1. So you don't really have to think about the power rule. So if you're taking the derivative of x with respect to x, it's just going to be 1. Now the next rule is the constant multiple rule. And in the constant multiple rule, I'm going to take the derivative of a constant times a function. So the derivative of a constant times a function is a constant times the derivative of the function. So let me show you how that works. If I want to take the derivative of the function 7x cubed, then that's just going to be the constant 7 times the derivative of x cubed. And so to get the derivative of x cubed, I'll use the power rule, and the derivative of x cubed is 3x squared. And then just multiply the 7 and 3 together and get 21x squared. On this example, and notice I used a different variable. I like to do that every now and then just to show you that the independent variable doesn't always have to be t. So f of t is 5 times the fourth root of t. Now we need to write this as a power, so the fourth root of t would actually be t to the 1/4 power. So now to find the derivative of this, I would have 5 times the derivative, and this notation here, I use this sometimes just to let you know that I'm about to, or if you want to use a good old Texan term, I'm fixing to take the derivative of this. So now in the next step, I'll go ahead and take the derivative of this using the power rule. So the derivative of t to the 1/4 would be 1/4 t to the negative 3/4. And then if you multiply that by 5, you get 5/4. So you're going to have 5 in the numerator, 4 in the denominator, and then when you move this to the denominator to change it to positive, you get t to the 3/4 in the denominator. Okay, so here we have 5 over x to the 7th, and I'm going to write that as 5 times x to the negative 7, and then the derivative of that would be 5 times the derivative of x to the negative 7. Now, be careful with these negative exponents, okay? So the derivative of x to the negative 7 would actually be negative 7 times x to the negative 8. Well, then I can multiply 5 times negative 7 and get negative 35. So I get negative 35, and then I can move x to the negative 8 to the denominator and get x to the 8 in the denominator. So that would just be negative 35 over x to the 8. Now, a special case of this constant multiple rule is that if you take the derivative of a constant times x with respect to x, then that result is just going to be the constant. So if you want to take the derivative of 7x with respect to x, you're just going to get 7. Okay, so that's just a direct consequence of that constant multiple rule. Now we have a sum or difference rule that says if you take the derivative of a sum, then that's the sum of the two derivatives. And then if you take the derivative of a difference here, then that's the difference of the two derivatives. So really this is kind of two rules in one. It's a sum rule and a difference rule. So let's find the derivative of a sum. So here I have the sum of a function 5x to the 4th plus another function 3x squared. So this tells me that the derivative, and I didn't put my little derivative sign there, so put a prime there. So the derivative of that is equal to the derivative of 5x to the 4th plus the derivative of 3x squared. So again, this just tells me I'm fixing to take the derivative. So the derivative of 5x to the 4th, we know that's going to be 5 times, and we can do some of this in our head, so watch this. I know that's going to be 5 times the derivative of x to the 4th, which is 5 times 4x cubed. And 5 times 4x cubed is 20x cubed. And then the derivative of 3x squared would be 3 times the derivative of x squared, and that would be 3 times 2x, which is 6x. Okay? Now on these next two, I'm not going to do this little fixing to notion here. I'm just going to go ahead and calculate the derivatives as I go. Now here I'm going to use z as my independent variable. So I have f of z equals 5z to the 4th minus 3z squared plus 7z minus 1. Now, if I need to take the derivative of this term by term. So take the derivative of 5z to the 4th. Well, that would be 5 times 4z cubed. So that would give me 20z cubed. And then minus 3 times z squared, well, we know that's minus 3 times the derivative of z squared. So that's minus 3 times 2z, which would be minus 6z. And we just learned this rule up here that the derivative of 7z with respect to z is just 7. And then we know the derivative of negative 1, since 1's a constant, would be 0. So we would just get 20z cubed minus 6z plus 7. Okay, I've got one more of these. On this one, I gave you one that has terms that need to be rewritten. So here I have 6 times the square root of x, which can be rewritten as 6 times x to the 1/2, and then plus 4 over x to the 5th, which can be written as 4 times x to the negative 5th, and then minus 1 over x to the 2/3, which can be written as minus x to the negative 2/3. Now, to take the derivative of 6 times x to the 1/2, it's going to be 6 times the derivative of x to 1/2. So now let's see, what's the derivative of x to 1/2? Using the power rule, I get 1/2 x to the negative 1/2. And then now we have 4 times the derivative of x to the negative 5. And what's the derivative of x to the negative 5? It's actually negative 5 x to the negative 6. Looks like I got a little typo there. So it's negative 5 x to the negative 6. And then take the derivative of minus x to the negative 2/3, and then you're going to bring down the negative 2/3, and since that's a minus, you're going to have minus a negative 2/3, which is plus 2/3, x to the negative 2/3 minus 1, which is x to the negative 5/3. And then the rest of this is just cleaning this up, and so I have 6 times 1/2, which is 3, and then I can move my x to the negative 1/2 in the denominator and get x to the positive 1/2, and then up here I get negative 20 x to the negative 6, so I'll need to correct this here as well. So that would be minus 20 over x to the positive 6, and then I'd have, for the last term, I'd have plus 2 over 3x to the 5/3 by moving the x to the negative 5/3 to the denominator. Okay, I'm going to finish this video with the trig differentiation rules, and I'll just let you look here. Here's your 6 trig functions, and over here are the derivatives for each one of these trig functions. So the derivative sine x is cosine x, derivative cosine x is minus sine x, and so on. Okay, so make sure you know these formulas for the derivatives of these trig functions. Now, I can't do a whole lot with them right now, but once we get the chain rule later in a later video, we'll be able to take derivatives of more complicated trig functions. But right now I have to keep it pretty simple. So here, if I want to take the derivative of this function, f of theta equals 5 sine theta times plus 3 tangent theta. Well, we know the derivative of 5 sine theta is just 5 times the derivative of sine theta. And up here it tells me the derivative of sine x is cosine x, so the derivative of sine theta would be cosine theta. So that'd just be 5 times cosine theta. And then the derivative of 3 tangent theta, we know the derivative of tangent theta up here is secant squared theta, so the derivative of 3 tangent theta would just be 3 times secant squared theta. And then the next one here, 5x cubed, the derivative of 5x cubed is simply 15x squared, and then minus secant x, so the derivative of secant x is just secant x tangent x, so that would be 15x squared minus secant x tangent x. And then the last one, I have 5x minus cotangent x, and so the derivative of 5x is just 5, and the derivative of cotangent x is minus cosecant squared x from up here in your table. And then so I have 5 minus, I have a double negative here, so that's going to change that to positive. So I'm going to get 5 plus cosecant squared x for the derivative. Okay, now in the next video, I'm going to go to the first rule, and it shouldn't last as long as this one did, but the next video is going to be the product rule, and then after that I'll do a video on the quotient rule.